welcome to How to Shrink My FPGAs, which is about optimizing the tile interfaces and the configuration logic in FABulous FPGA fabrics. That's work done with Kelvin, Nguyen, Jing and myself. Okay, what's the FABulous framework? It's a fully integrated framework to generate FPGA fabrics all the way to the ASIC down, as well as parameterizing the toolchain that you need to compile your own circuits into bit streams that then will run on that FPGA fabric. There are more ingredients not shown in the figure for emulation, simulation and other things. The project itself integrates lots of other great open source work like JOSIS, ABC for logic synthesis technology mapping. We use NextPNR or VPR for routing, Open RAM here for our RAM blocks, or very later for simulation. Okay. And in this paper, we look specifically into the ASIC implementation aspect and the physical implementation of that one. And if you want to see more about FABulous, go on our Git repository. The whole project is open source under Apache 2.0 license, and you will find more information on our documentation website. Okay, but now back to our project here. When we implement FPGA fabrics, we implement them from tiles. What you see here is a CLB tile, the yellow parts here at the border, these small triangles that are our interface wires, and tiles are designed such that an input on one side corresponds to an output on the other side, so that you can stitch those tiles together to form a fabric at the end of the day. That gives you consistent timing, very reliable implementation, and if you do some handcrafting inside the tile by copy and pasting, you can reuse that optimization effort across the entire fabric. And another interesting one is that thanks to the Google Shuttle program, they do way more than just offering free silicon. They build an ecosystem also around open source PDKs, and that allows us to basically share GDS macros, and that means that using, for example, that Skywater 130 nanometer process, it will allow you to implement FPGA fabrics just from such pre-compiled macros, rather than going all the way to tiny standard cell or whatever elements, yeah? So that makes life very, very easy. It's a big advantage. Okay. We all know if we implement such an any FPGA, that routing is dominating the area. Yeah, all those switch matrix, multiplexers, configuration cells, that is all very expensive. So if you can do something there, this will define if you win or lose. Yeah. So what you really want to do is you want to use cheap multiplexers, for example, pass gate multiplexers or transmission gate multiplexers, and you want to use anything that's cheap for configuration storage, because just the configuration bits themselves contribute considerably to the total area that you need. Okay. So if you want to build such a tile-based fabric, the way how this all works is that if we don't have any other constraints, we just pragmatically start with implementing the CLBs first. We try to build the smallest square that fulfills the resource requirements and gets it routed. Yeah, and that will define the height for all the other tiles. Yeah, where a tile may, or a resource may still use the height of multiple CLB tiles. Yeah, like here our DSP tile is double the height of a CLB. Yeah, and the exact width is defined by how much resources each specific resource type really needs. Yeah, and that allows you to build overall a very dense fabric. And that's the trick actually everybody, including all the big industry players, play. Okay, now what we started was just looking here at CLBs. We replaced the standard cell multiplexers with our own custom multiplexers. And to make life easy, the FABulous routing fabric is mostly designed around MUX4s, yeah, for input multiplexers. And that's not unusual. There is somewhere a sweet spot by using 4 input multiplexers. And even if you would look in recent silence FPGAs like ultra-scale devices, they mostly use MUX4s throughout the entire fabric for virtually anything. And so we looked into how much area we may potentially gain, and well, it's easy to compute. You just take the area of a standard cell MUX4, right? We subtract this with our custom multiplexer, right? And that multiplied by the number of MUX4 multiplexers that we have gives us the possible area saving, what we would kind of expect if we play that game. However, if we run the experiment and we take our standard cell area here, the black column, as a baseline, then we see if we replace this with custom 4 multiplexers that the area is not anyhow shrinking as much as we expected. And if we repeat the experiment for register slices or DSP slices, we see there is virtually no improvement at all. Yeah, what we see instead is that the core utilization goes down. The core utilization is within the area allocated for our CLB, how much of that area is actually used by standard cell or custom cell elements. Yeah. So here you see if we use custom 4 multiplexers, we leave round about 40% of our area actually unused. And that's an indicator that our tile routing is very congested. Yeah, so here we are not bound by logic on the die in the bottom. We are bound by the metal stack on top that you need to get it routed, and the tool is not able to squeeze things more densely together because otherwise it wouldn't get routed. Okay. The trick we applied is when we analyzed the final netlist and the congestion to see what can we do about it, we saw an effect that is shown here in this figure. If you connect your configuration latch or flip-flop to, let's say, a switch matrix multiplexer or a lookup table, that will create kind of a pull force. Yeah. So here you want the tool tries to use a short connection, also of course to get congestion down, between this configuration cell and the multiplexer it controls. And that may result in an inferior placement. Yeah, like here you see this yellow multiplexer that would be better off. It would be placed a little bit further to the right because all the other terminals are located further to the right, right? And here the green multiplexer, there's the same situation, just the other way around. So if we could somehow rewire which configuration bit controls which resource, we will get to a routing that looks much less congested as like here in this example. Yeah, and what we did here is like that we took, in this case, configuration bit 0, not controlling M0 anymore. We use it to control M1, and that allows the tool to get this better placement and corresponding routing implemented. Yeah, and if we play this game, we also have to remap the bitstream data. Yeah, of course, if M1 here is controlled by a 1, yeah, we have to ensure that this is in the original and after the modification still the same. Okay, what I showed so far was for shift register configuration. Yeah, that means you use D flip-flops or anything like that, and you daisy chain all your configuration bits in a long chain, however you link this together, yeah, and that forms your configuration bit stream. And the optimization basically changes which of these bits gets then connected to which specific multiplexer or let's say a lookup table, yeah, depending on what the configuration cell here is actually controlling. FABulous is the only open source framework at the moment that has been shown for frame-based configuration. And how does that work? You have a long basically deserializer to generate a wide configuration word. So these are my configuration data, and then you can strobe it into cheap configuration latches, yeah, and the latches are decided by a column decoder, yeah, and if let's assume that this would be a CLB inside your fabric, yeah, then a CLB needs typically a few hundred configuration latches, so that means you also have a couple of frames and you would configure them one after the other. You get the idea. Our optimization with bitstream remapping works slightly different for the for frame-based configuration. Here we allocate which grid point, which is defined by a specific frame data bit and frame strobe. Yeah, so if we say that this is one configuration bit and this is a specific frame strobe, then this defines a cross point, and we define which cross point will connect to which configuration latch. And this is how we do the bitstream remapping for frame-based configuration. And the algorithm that we use is not even done by ourselves, as we thought, oh, this is probably a standard optimization problem, somebody has done this. And yes, there is a Google library that we use, yeah, from operations research tools from Google, and what our contribution here is mainly how to model it. Yeah, so we model our grid points. These are again in horizontal direction our individual frame data bits, right? In the vertical direction we have our individual frame strobe signals, and these cross points here are our grid points, and then we have our fabric where we have somehow our latches, and we connect which latch will be actually connected to which grid point. And this library or the algorithm ensures that we will always find a feasible solution, which is always possible if we have at least as many grid points as we have latches, even if we have situations like here with clusters and so forth. And if we run all this and plot down connections between the different cells as after implementation and after the optimization that we run, you see something that looks like this. Here in the top row we show the frame data wires before and after optimization, and in the bottom it's frame strobe. The numbers here just refer to physical cell dimensions in micrometers. Yeah, the dots here are the positions of our configuration latches. Yeah, and you see that the optimizations use much less wiring. Yeah, so this figure looks much less busy than here on the left hand side, and again this corresponds, you see this for frame data as well as for the frame strobe signals. Yeah, and we did all kinds of experiments. All the details are in the paper. Yeah, and when we started, we took our submission that we submitted to the Shuttle 2 run, then we replaced with custom 4 multiplexers, and we only see a difference of 3.8% because of that one. Then we saw, okay, this is all the problem is why we haven't got denser is due to congestion. So we activated an extra metal layer. Normally in FABulous, if we would do embedded FPGAs, we leave 1 or 2 metal layers unused that you normally need for the system level integration. Yeah, so think about you want to build an SoC and somewhere in the middle you place a FABulous embedded FPGA, then you don't want to have that this fabric is an obstacle for the rest of your system. Yeah, so you need like at least 1 or 2 metal layers for the top level integration. But if you don't want to build an SoC, you say, okay, I just built an standalone FPGA, then you may use all metal layers. And if we play that game, we get something like 12% better in area. If we do the bitstream remapping, we got 19.4% better. Yeah, meaning that the bitstream remapping is actually helping more than an extra metal layer, which is quite substantial. Yeah, as this is an optimization that comes for free. If we combine both together, the bitstream remapping and the extra metal layer, we only gain another 2%, which is typically not worth to spend that extra money. We also looked into shift register configuration because FABulous can generate a frame-based configuration, that's here on the left, and shift register configuration, that's these 4 columns here. And we used standard D flip-flops as a baseline, and then we looked like after applying our bit tree remapping how much we could gain, and the gain was very little here, it was just a few percent. And the reason why it's not more is very simple, because the D flip-flops are so big, they will force the tile to be big, so it gives you a lot of space for getting the routing implemented, and by definition such a design is much less congested. Yeah. There is another open source FPGA project called Open FPGA, and they try to mitigate the huge cost of D flip-flops by providing custom flip-flop cells, which are not really smaller than latches as we use in FABulous. But we played the optimization game for an assumed architecture that would have a chip that would use those custom cells, and even with those optimizations, it is still worse than what you could get from frame-based configuration. Yeah. Another optimization we looked into was pin swapping. I showed this picture of a CLB tile with all the interface ports at the surrounding, and if we just move the allocation to those interface ports, this has of course impact on the physical implementation, ergo it is an optimization game we can play. So we shuffled this around, and the algorithm and what we did is described in the paper, and we saw an improvement that is pretty much as good as what we got from the bitstream remapping. And the good news is we can apply this both together, which gives us in total almost a 22% improvement in area, which comes entirely for free. And at this improvement in area, we get to a core density close to 90-91%. That means this is almost as good as it can be. Yeah, we will never reach 100% anyway. Yeah, so this is showing us that the optimization is doing a great job. Okay. Other paper contributions that I will not go into much detail due to time constraints is we consider a full flow that considers the RAM, DSP or whatever other block that you have, because there are some dependencies, and that describes how it's resolved. I mentioned the impact on metal layers, but there is more, that we also look into the routing demand created by different channel capacities. Yeah, think of you route a wire, let's say, to just the next adjacent CLB or to a CLB that is much further away. That has impact on how much routing or wire resources you use in the metal stack, and we examined the impact of that one and how this can be dealt with. Yeah. I mentioned the tile interface optimization, but in the paper is also the algorithm and how we did this. We have some figures on timing in the paper. We don't have anything on power, as we don't have reliable enough estimates for that one, but we can probably assume that power will be better, because if you have shorter wires, you have less parasitics, and that will typically help you. And the paper provides a discussion about frame-based versus shift register configuration. A brief summary on that one is that frame-based configuration is always winning, as it's cheaper to implement. It's the only way to really implement partial reconfiguration. Yes, there are some people doing shift register configuration, or basically every other open source project on FPGAs does shift register configuration, and they claim that they can bypass shift register chains to do partial reconfiguration, but that has a lot of limitations and will fundamentally not work. Also, frame-based configuration is way more versatile, and to give you an idea, we just taped out our first memristor FPGA where all the configuration latches had been replaced by ARM cells, and that could only be done by using frame-based configuration. Okay, last slide. I mentioned our baseline, that's this tile I circle with my mouse, was a shuttle 2 FABulous submission, and at the same shuttle submission there was also an Open FPGA design. Yeah, so we have two competing designs taped out in the same process. Yeah, of course, both designs have submitted not a CLB alone. That was always a full fabric, of course. Yeah, but here I just compare the tiles against each other. The implementation problem, the physical implementation problem that between Open FPGA and FABulous was round about the same. FABulous uses a few multiplexers less, something like 8% less multiplexers, but we use like 14 or so percent more configuration latches, and so meaning that the area requirements for both are round about the same, but nevertheless Open FPGA, because they have to use expensive D flip-flops for the configuration, or rather they're using cheap latches, they are almost 20% bigger in area. Yeah, and when we started with our optimizations as described in this paper, we could shrink our fabric by another 20-something%, which gives us almost a 40% area advantage over Open FPGA at the moment. And this is making our fabrics to the most area efficient ones you can get from any open source framework at the moment. Okay, that's all the content I wanted to provide in this small overview. More is in the paper. I want to say thanks to all the contributors making this work possible. This includes, of course, also all the external fantastic open source projects we rely on. Thanks also to our sponsors, EPSRC, as well as Google for sponsoring the FABulous Open MPW shuttle program. And if you want to see more, follow us on GitHub under our repository. Thank you, and happy configuring.